Thank you, Jen. Well, it's been a real privilege and honor to be able to work with great, fellow researchers at the Institute. So I will talk about the environmental and resource impacts of renewable energy technologies. Again, my name is Sangwon. I'm an associate professor at the Brand School of Environmental Science and Management, and I have been doing life cycle assessment, which is a tool for quantifying environmental impacts of product and technologies over the last 18 years. So as a background, the issue is the electricity. So electricity is the most rapidly growing delivered energy throughout the world. And what you can see here is that, well, this is the projections for delivered energy consumption growth. And as you can see, the electricity is growing much faster, not only in the United States, but throughout the world. And at the same time, electricity generation is the largest source of anthropogenic greenhouse gas emissions. And in order to achieve 2-degree target that is recommended by the IPCC, a radical decarbonization of electricity is really crucial. The question then is that, well, are low carbon electricity technologies sustainable? Meaning that, well, we have to scale up the low carbon electricity generation technologies greatly in the future in order to meet the 2-degree target and also reduce other environmental emissions. Then are there any unintended consequences in terms of the environmental impact or resources need for supplying that amount of green electricity, I would say. So environmental and resource due diligence, as we termed, and is there any unintended consequences or are there any trade-offs? So in the past, there were studies about 1 or 2 technologies and considering 1 or 2 environmental impacts or resources. But we'd like to think big, and we wanted to cover about more than 2 dozens of technologies, covering all the geographical regions of the world, and covering about a dozen and a half different environmental impact categories. So we wanted to have a kind of level ground assessment on the environmental and resource implications of those renewable energy technologies compared with the conventional fossil fuel energy technologies with or without CCS. So the project was commissioned by the United Nations Environment Program and was led by Edgar Hartwich in Norway, NTNU Norway, and myself. And to our best knowledge, this would be the first global scale time series life cycle assessment study that covers a wide range of low carbon electricity technologies. So what are the technologies that we are covering? We are covering a number of different PV technologies, polysilicon roof type, polysilicon ground type, 6 roof and ground types, and cadmium telluride roof and ground types, concentrated solar power tower and trough type, and hydro, there are 2 different types of them, and wind power, there are different ways in which we can kind of anchor them in the offshore still bases or gravity bases, which is a chunk of cement that is pressing the bottom of the ocean. And there are a number of coal power technologies with CCS and without CCS, and also natural gas technologies are compared. What are the environmental impacts and resource requirements we have analyzed? Global warming, acidification, eutrophication, ozone layer depletion, and all these toxic impact categories, as well as some of the metal categories like iron, copper, aluminum, cement. No, cement is not really metal, so other resources input and also fossil energy input to those processes. This type of work tends to be very data intensive, so we had to gather around 50 scientists all over the world, representing 50 different nations, and we actually analyzed over 1 million data points gathered from various different sources, including private sectors, research institute, national governments, and international agencies, including IEA. And we were using IEA's Blue Map scenario, and Blue Map scenario is now being revised into, with a different name called the 2-degree scenario that is aligned with a 2-degree target set by IPCC. This scenario is a progressive renewable energy scenario. It's realistic but very progressive. It is based on the assumption that, well, electricity demand will be doubled by 2050, and solar and wind combined will share about 40% of the electricity grid by 2050. Currently, the solar and wind combined represents about only 3% of the electricity grid. Technology development and efficiency changes. We have looked into the NREL's National Renewable Energy Laboratory's most recent technology roadmaps for these technologies so that we understand better about what will be the materials requirements and energy requirement for those technologies. So I will show you the results. So results will be shown in two different formats. One is the per kilowatt hour electricity result. And the other one is a total result overlaid with the blue map scenario. It will be very nice to have a fuel cell technology someday here. Okay, so first, this is the per kilowatt hour result only for the global warming potential. So what we are seeing here is, in general, photovoltaic technologies are much lower in terms of the kilowatt hour of greenhouse gas emission, which is very intuitive. The reason why there is a little bit of range here is that we have gathered this information from various different sources, various different companies, very different regions. So China, United States are different in terms of the electricity grid mix and efficiency of the material consumption. So that's what this range is representing. But in general, PVs are much better as compared to coal power plant without CCS. And even with CCS, it cannot really it's not really comparable to renewable energy technologies. Concentrated solar power, also very good. Hydropower, pretty good. Wind power, also very nice in terms of the greenhouse gas emissions. Even the efficient natural gas power with CCS cannot come up with the same level of greenhouse gas emissions with renewable energy technologies. Looking into the other environmental impact categories, this is global warming, eutrophication, ecotoxicity, particulate matter emissions, and land use change. And these are all the different material consumption. So general picture here is that, well, those renewable energy technologies are performing better than fossil fuel counterparts. One interesting thing here is that, well, CCS, applying CCS will actually increase some of the environmental impacts other than greenhouse gas emissions. So it is reducing greenhouse gas emissions at the cost of increasing other environmental impacts. There are some trade-offs with CCS. Interesting result here again is that, well, in terms of the material consumption, iron, cement, aluminum, copper, we are seeing higher demand on those materials by some of the renewable energy technologies, especially solar and wind. I see that the Copper Development Association is part of the sponsor here, and we were surprised that how important copper is in order to enable a significant increase in renewable energy technologies in the future. This is the total impact over time laid over with the blue map scenario. The general trend here is that according to the blue map scenario, which is a progressive renewable energy technology scenario, most of the environmental impacts are decreasing over time, as we can see here. However, the natural resources consumption is expected to rise over time because of the fact that those renewable energy technologies tend to be more material intensive. So main conclusions out of this research, we hoped to be able to publish this very soon. We are on the second round of revision for the proceedings of National Academy of Science, and I'm confident that we will be able to publish this soon. The main conclusions are that, well, renewable energy electricity generates about 90% less environmental impacts per kilowatt hour compared to modern natural gas combined cycle in general. And carbon capture and storage, CCS generates 20 to 100% more non-CO2 emissions compared to current fossil fuel electricity. And there will be more pressure on materials as we increase the portion of renewable energy in our electricity grid. And however, the additional bulk material needs are within the manageable range. So we are not really talking about the materials requirement that is not manageable in the future. So in general, very positive result toward renewable energy electricity. And we are working on our second report here. We are focusing on energy efficiency technologies, including LED. John just talked about those LEDs, and it's really fascinating to see those efficiency growth. And what are the implications of applying those efficiency technologies toward the 2050? Would be the question that we are asking. So we are looking into a variety of different types of efficiency technologies, which I will show you a little later. And we'll publish a special issue in April 2015. And the UNEP report will be launched in early 2015, combining the first report and also the second report on efficiency technologies. So what are the efficiency technologies that we are looking into? We are looking into building, mobility, and industry divisions. And each of those divisions, we have different functions that are fulfilled by various different technologies. For example, if we look at the lighting, LED fluorescent, compact fluorescent is the topic of our research. Mobility, we are looking into various different types of mobility technologies. Industrial technology, we're also looking into the copper smelters, aluminum smelters, and iron and steel production facilities as well. So that's about it, and I would like to acknowledge my co-authors here. Here are a number of people that we work together representing various different institutes and countries. Thank you.